Okay, so so last week we talked about this spectrum analysis problem. Okay, so the task is to find out this frequency fi. Okay, from these observations yt, right? And we define this for convenience. Define this zi being this exponential 2 pi fi, right? Then we show that we by collecting this data, okay, using this rolling window to put this yt, right? So we collect d samples, right, and next d samples, next d sample, and this in this rolling window fashions, right? And for each of them, we put into a matrix, right? You still remember? Then we can write this as a matrix Y times A D S plus W. Okay. And this Y is D by T, right? It's D by T. And A is D by K. K sources. D is K by K. Right? And S is K by T. K by T. Right? So that's the dimensions. And the A and S are quite special, right? A has this structure. Right? A is a matrix like this, okay, which is D by K, right? D by K. And similar S is like a transpose versions of A, okay, but with the dimension is not the same. Okay, right. So any problem of for obtaining this from here? Right. So as I say, it's basically we collect this data, okay, this rolling window fashion, and then put them into this matrix Y. Then you can write the model, right? A times D S, okay. And the information, right? We want to figure out is this Fi, or equivalent is this Zi, okay, which are contained by this A and S, right? It's A and S. Okay, so first of all, we'll see that these matrix A and S are special matrices. They are called these Vanderman matrix. Okay, so it has some very strong properties. Because this is a M by N, okay, Vanderman matrix. Okay. So here we have Z1 to Zn and to the power of n minus. Okay, so it's an n by n matrix. Then key property is that this matrix, this type matrix, is always full rank. As long as this Z1, Z2 to Zn are different. Okay. As long as Z1, Z2 to Zn they are different, then it will be full rank. Okay. If m is larger than n, then its rank is n. If n is larger than m, then its rank is n. Okay, so it's always full rank. So, and we can utilize this property. Because we will utilize this property to have an algorithm to search the z. Okay, allow us to search the z. Okay, so that we can find this z1 to zk, or equivalent in the f1 to fk. Okay. So why this matrix is full rank? Okay, let's prove this. As always, right, we can use contradiction. Suppose not. Okay, suppose not. If Z is not full rank, then Z transpose is also not full rank, right? It's not full rank. Okay, to show this is sufficient. Okay, because suppose n, okay, is less than n, for example. Okay, so this is a matrix. Okay, then it's sufficient to check out the first k, any k, okay, first m by m, m by n, right? Or any k, any submatrix, any square submatrix. It's sufficient to check this. Right? K can be m. K can be m is m by n. Right? So it's fine to check. Okay, let me use this m by n. So I mean, it's sufficient to check this submatrix, square submatrix. Right? If it's square submatrix full rank, right, then Z is full rank. Right? For example, this m is less than n, then we check this m by n matrix. If it's full rank, then Z is full rank. If the other case, if m is larger than n, then Z is a whole matrix, right? Then again, we can check this m by m submatrix, right? To check this is full rank, then it's full rank. The whole matrix full rank. Okay, so it's sufficient to check a k by k square submatrix. Okay. Okay, so it's sufficient to check k by k submatrix. Okay, k is the minimum of n and n. Okay, of z. Okay, sufficient to check k by k submatrix. So then let's denote this submatrix by zk. Okay, so which is z1 to zk, z1 to the power k minus 1, z2 to z2 to the power k minus 1, zk to the power k minus 1. Okay, so it's sufficient to check, right? Okay, so let's check out whether this matrix is full rank or not. Okay, whether this is full rank or not. Then prove this by contradiction. Okay, suppose not. So zk is not full rank. Well, it's not. If zk is not full rank, then zk transpose also not full rank, right? Because rank, a matrix, right? His rank is the same its transpose. So suppose it's not full rank, and or equivalent zk transpose is not full rank, then so we look at zk transpose, then exists a non-trivial solution, right? To here, to this, right? If it's not full rank, then it's null space, it's not empty, right? It's not on, it's more than 0, right? More than 0. Then exists alpha not equal to 0, so that it holds, right? It's null space, right? So if you look at the zk, right? Then zk transpose, each row of zk transpose, each column of zk, right? So this is equivalent, right? This condition is equivalent of we have, right? Alpha 1 plus zi, right? Alpha 2 plus, right? zi to the power k minus 1 alpha k, right? Equal to 0. And for all I from 1 to k, right? You see the first column, right? First column gives us the inner product. It's the first column with alpha, right? But inner product between first column and alpha is alpha 1, z1, alpha 2 to z1 k minus 1 alpha k, right? And second column or the second row of zk transpose with alpha give us zi, right? I equal to 2, right? And so on to get this k equation. So this means for this polynomial, you see, this is a polynomial. For this polynomial, right? If you look at this polynomial, this zi, z1, z2 to zk are the roots of this polynomial, right? So this polynomial has roots z1, z2 to zk, right? So this implies z1, z2 to zk are the roots of this polynomial, right? And here we assume z1 to zk, they all are different. They are different, which means this polynomial, right, has k different roots. But this is not right, right? Because this polynomial has order only k minus 1, right? So how can we have k distinct roots? Okay, so this is a contradiction. So contradict with the fact that rho z has order k minus 1. Okay, it's a polynomial to the, or it's an order only k minus 1, right? So it's impossible you can have k roots, different roots. So that's a contradiction. So which means zk, this cannot hold. Okay, this cannot hold, except the alpha is 0. So which means zk is full rank. Okay, so then we prove that this is true. Okay. Right. Okay. So you see that this, as long as this z1 to z, and they are different than this a or s, right? For A, for example, as long as the D is, right, because it's a D by K, right? This is always full ring. If D is larger than K, then this is full count ring, right? If D is smaller than K, this is full ring. Okay, so is S. So is S. Okay. Now we want to see is then with this property, how can we utilize this property to have an algorithm to search this Z1 to ZK. Okay. So suppose we want to do a very simple search and want to check whether we can find this Z1 to ZK. Then let's define this vector. Because this, each column, right, or each row has this special structure, right? So we define this AZ. It's a function of Z, right? Define this AZ as 1 Z, Z squared to Z to the power of D minus 1. So let's define this vector AZ. You see if Z is one of Z1 to ZK, then AZ, right, is one of the columns, right? It's one of the columns, right? So we see if Z belongs to Z1, Z2 to ZK, if Z belongs to Z1, Z2 to ZK, right? If Z belongs to Z1, Z2 to ZK, then obviously AZ, right? AZ is one of a column of A, right? One of a column of A. So AZ will belong to range space of A, right? It's quite obvious. Then the question is whether if this direction can be true or not. If you find a Z and you find out that AZ is belong to a range space of A, and we wonder whether the Z is one of the solutions. Okay, one of the correct Z's we want to find out. Okay, if this is true, if this can be true, then this gives us a very simple algorithm, right? We can search if this is true, then we can, if this is yes, then we can search, right? We can search Z, right? We can search Z, or it's equivalent search F, right? Search this. It's F, right? Because Z is exponential J2 pi, right? Zi is Fi, right? So search a Z, right? Or equivalent, we can search F, right? We can search each F give you a Z, right? So if yes, then we can search F, search a frequency, and to check whether the AZ, right, belong to range space of A or not. Okay, right? So if this is true, then we can do something like this, right? Do something like this. So any problem with this? Right? If this can be true, if AZ if we have a Z and we find that it belongs to range space of A, and then it's one of the solutions, right? And if this can be done, then this is true, then we can search a Z, right, by checking whether AZ belongs to range space, right? Then that's an algorithm we can to search these solutions. Is that okay? Right? So then of course, we will show that this is true. Okay, it's quite surprising. If the Z is belong to range space, it must be one of the Z1 to ZK. And you will see this is due to this property 4, because it's always for range. So there's a theory, I forgot the number. Okay. It says that we assume D is no larger than, is no less than K plus 1. Okay. D is greater equal to K plus 1. Then Z belong to Z1 to ZK if and only if AZ belongs to a range space of A. Okay, so the if par, right? Only if par is this direction, right? We already see this is quite obvious, right? If Z is one of the Z1 to ZK, then AZ is one of the columns of A. And of course, it's in the range space of A, right? So let's see this part. If AZ is in the range space of A, then Z must be one of the Z1 to ZK. Okay, then again, suppose not. Let's see if not, then what's going to happen? Suppose not means that Z is not belong to Z1, Z2 to ZK. Okay, Z is not one of the Z1 to ZK. Okay, then you put the AZ in here with A. You put here. Then what's the dimension of this matrix? This is a D by K, right? A is D by K, right? Now you augment AZ here, okay? Then this is a D by K plus 1. D by K plus 1. Okay, D by K plus 1. Right. Then you look at this one. A is in the range space of A. Means what? A is a linear combination of colors of A. Right. So which means this matrix is what? Is rank deficient, right? Will not be full rank, right? Is not full rank, right? Right. Then this matrix is rank deficient. But then this contract takes with property 4. Because Z is not one of the ZK. Z is not one of the ZK. So this should be full rank, right? Right. This contradicts with property 4. You get conclusion. You get the proof, right? If AZ is in the range space, then this should be rank deficient. Then Z must be one of the Z1 to ZK. Okay. Otherwise, if Z is not equal to any of them, then this should be full rank. Okay, this should be full rank. And any questions here? Right? So then this is right? The proof is not difficult, but it's very very critical, right? See these observations. So then, as I say, right? So you see Z, we can search the Z, search Z1 to ZK, right? Find out whether this Z1 to ZK, where they are, right? By checking AZ is in the range space of A, right? But we don't have range space of A, right? Because we only have is Y, right? All we have is Y. All we have is Y. So then we need to connect we need to find out where we can, right? Find a way so that we can check AZ is in the range space of A, given without knowing A is, okay, because we actually, A is actually what we want to find out, right? This. So we only have Y, okay? We only have Y. We only have Y, okay? So we next is we try to see how is the range space of A connect with the Y, okay? And so here we compute the correlation matrix. Okay, it's YY Hermitian, right? YY Hermitian, and divided by 1/T. So this is computing the sample correlation matrix, right? So Ry is 1/T ADS plus W. It's ADS plus W Hermitian, right? Right. So this will give us photons, right? 1/T ADS S Hermitian D A Hermitian plus 1/T ADSW Hermitian plus 1/T W ADS plus W. Right. Photon. The key, of course, is in the first term, because these terms are corrupt by noise, or this is purely noise, right? So in the highest NR, right? If it is higher than we can ignore this three terms, or if you assume that this WT, okay, these elements in this matrix W, they are zero mean, okay, independent, identically distributed, zero mean, okay, and its variance or power is sigma W squared. Okay, that's some standard assumptions. And under this assumption, and if T is large enough, then you know that this by the law of large numbers. No, not law. This what's the same? Yeah, law of large numbers. It will converge to its mean, statistical mean, right? Will approximate to 0. Okay, and this one will approximate to identity matrix. Okay, identity matrix. So either if noise power is small, then you can ignore this one, or is if a t is sufficiently large, then this will get close to 0, and this will get close to an identity. Okay, so we can approximate this by a d 1 over t s s formation d a formation plus sigma identity. Okay. Okay, so we can compute this ry, right? And look at this one, this term. So we can, the inside this term is, we call it phi, okay? So this is 1 over t dss summation d, right? And here we made some minor assumptions, right? It's first of all, of course, this alpha I will assume they are non-zero. Okay, so this d is diagonal is this alpha 1 to alpha k, right? This is a d is an invertible matrix. And also this frequency are not the same, right? So this is also we made the assumption that this z1 to zk are not the same. Okay. And we also here we also assume that z is greater equal to k plus 1. Right? D is greater equal to k plus 1. And here we also assume t is this will be, if this is true, then this will be true. Okay. T is greater equal to k. Okay. T is greater equal to k. Okay, T is greater equal to k. You see, then S is a full row rank, right? S is a full row rank matrix, right? So this matrix, right? As we actually improving the in the proof of CC Hermitian equal to BB Hermitian, right? There's one property proving this. We already showed that, right? If this is for current rank and C Hermitian, C is right, is invertible. So this is similar to that one, right? Because S is full rank, so you can find that S Hermitian, right? This is full rank. Right, full rank. Actually, because this S has Hermitian, so it's a PSD matrix, right? It's a PSD matrix. And it's full rank, so it's a PD, right? It's PD. And this D are, because, right, they are diagonal invertible, so the whole matrix is PD. Okay, the whole matrix is PD. Okay. Right, this is PD, and this square invertible, then this will be PD. That's one of the property we mentioned before, right? So it's a correlation matrix is A phi A formation plus sigma W identity, and here phi is PD. Phi is PD. Right. Then you further look at A, right? A is rank, it's full count rank, right? Because we assume D is greater equal to K plus 1. So D is greater than K, right? D is greater than K, so A is a whole matrix, right? A is a whole matrix. A is a whole matrix. It's D by K, right? Right, and it's a fundamental matrix. So we know its rank is K, right? rank is K. So A is full count rank. And A Hermitian will be full row rank, right? A Hermitian will be full row rank. So this will be full row rank. Right? So A is full row rank. Phi is PD, so invertible. So phi A Hermitian will be full row rank. Right? Phi A Hermitian will be full row rank. And so this is the full row rank matrix multiplying the right hand side of A. And we have one property, right? The range space of A is the range space of this matrix is the same as the range space of A, right? So you see, so here we get the range space of A is equal to a range space A phi A Hermitian. Okay, because this is full row rank. Okay, phi A Hermitian full row rank, and we have one property. Right? Property 2, right? By property 2. By property 2. Okay. So so this means that, right, the range space of A is equivalent the range space of A phi A Hermitian in here, right? Inside of this correlation matrix. And the moreover, its rank, right? Its rank is will be the same, right? It's K. Rank is K. So this A phi A Hermitian, right, which is a D by D matrix. Okay, it's a D by D matrix. Its rank is K. And its range space equal to A. Okay, the rank is K. So this means that the EVD, you consider the eigenvalue decomposition of this A phi A Hermitian. Now you know the rank is K. So it has K non-zero eigenvalues. And it's a PSD matrix. These eigenvalues are non-negative, right? So which can be written as B lambda 1 to lambda K and 0, 0, 0 B Hermitian, right? And where lambda 1 to lambda K are actually not positive. Okay. Because you know its rank is K, right? K non-zero eigenvalues. Right. So this means, right, this eigenvalue, the first K eigenvalues are non-zero. So we can partition, correspondingly partition, look at these eigenvectors associated with these eigenvalues, right? So you can partition V into V1, V2 into 2 parts, right? V1, V2. And this V1 will be D by K, and V2 will be D by D minus K, right? And so you substitute this partition into here, so you see that A phi A Hermitian, right, actually can be written as V1 lambda 1 to lambda K V1 Hermitian, right? Then from here you see, right, V1 is what? It's semi-unitary, right? It's semi-unitary. So this is full count rank. V1 is K orthogonal columns, right? 4-count rank. This 4-row rank, this is invertible. So again, this is a 4-count. This is a matrix multiplied with a 4-row rank matrix behind it. So the range space of this matrix or this matrix is the same as the range space of V1, right? It's the same as range space of V1. So we get that range space of A phi A Hermitian. We already know is equal to a range space of A. Now we see it's also equal to a range space of V1. Also range space of V1. It's all range space, right? While we look at the eigenvalue decomposition of this A phi A Hermitian, that's because the Ry, right, is A phi A Hermitian plus an identity. So basically the eigenvectors of A phi A Hermitian is the eigenvector of, right, the whole Ry, right? So you see the Ry, right, is equal to A phi A Hermitian plus sigma W identity, right? Now A phi A Hermitian can be written as V, right, for this lambda V Hermitian plus sigma W identity, right? So this is an EVD of A phi Hermitian. And identity matrix, right, we can replace this by VV Hermitian, right? We can replace by VV Hermitian, right? Because it's unitary. So this is V lambda plus sigma W identity, V Hermitian, right? This is a diagonal, right? So which means that this is the eigenvalue decomposition for the correlation of Ry. Okay, and this is equal to lambda 1 plus sigma W squared to lambda K plus sigma W squared and sigma W squared to sigma W squared. Okay. Then this gives us a way to find out the basis for range space of A, because we need to know, right, the range space of A, right? We want to know the range space of A, be able to check whether AZ belong to range space of A or not. Using this to find out the Z1 to ZK. And here tell us the range space of A is equal to a range space of V1. Okay, so it's equivalent to find out the range space of V1. And how can we get the range space of V1? Right, this tell us we can do the eigenvalue decomposition to Ry. Then, 哇，已经够破烂了。Right, then we can get from here. Get from here. So we can do the eigenvalue decomposition for Ry, right? And for these eigenvector associated with these first k eigenvalues, this V1 is this V1, represent the range space of A. Okay. So this gives us a way we actually doesn't know A, right? We only have Y. But by Ry, the observation matrix, this correlation matrix, to do the eigenvalue decompositions. Then find out the eigenvectors associated with the first k eigenvalues. These V1, okay, these columns give you this match V1, which have the same range space as range space of A. Okay, in space of A. And how can we get? Is also here. You also see there's a. Here we assume K is known a priori, right? We assume we know K, how many sources. Actually, there's a simple way, right? We can check how many Ks if the node is not too large, because you can see here, right? By doing the eigenvalue decomposition and you check out its eigenvalue distribution, you should see the first K, they are larger than the last, because these only contain the noise power, but here is noise power plus the signal parts. Okay, signal parts. Okay. So a simple way to check to get what the value K is that you check its eigenvalues, and you should see a significant gap, okay, between the K's eigenvalue and K plus 1. If the noise is not too large. If the noise is very large, then it's difficult to see the gap, right, between these signals. So that's why, because this part contains only the noise, this part contains the noise and signal. So we call, in signal processing, people call the range space by V1 is called signal subspace. And the range space of V2 is called noise subspace. Noise subspace. 这个有点 misleading 啊，因为 noise actually is everywhere. Because noise covariance matrix identity. Identity means what? It's everywhere in all directions. Okay, in all directions. But by here, right, what we call it noise subspace, because it means that this part contains purely have noise. A single subspace associated with this part, which actually is signal corrupted by noise. Okay, corrupted by noise. Okay, so now we see we can use by EVD. Right, by EVD of Ry, then we can get the basis, right? Because V1 is a basis for range space. Right, so we can use this. We check AZ belong to the range space of V1, right? We check this, and we know that, right, because range space V1 equal to range space of A. So if AZ for this particular Z, AZ belong to range space of V1, then that Z is one of the Z1, right? We have proved that. So how can we do this? This is not easy to do, right? So equivalent, we can alternatively we can change this to AZ inner product with V2 should be 0, right? Because V1 and V2 they are orthogonal complement. So if AZ is orthogonal to V2, means AZ is belong to A1. Then this one is easier to check. So, right, we can have an algorithm. The algorithm is to, right, is to search the F right? So this algorithm is called music. Is that given this right, we have this Ry and the K less than D, okay? Then we perform EVD of Ry, right, to obtain V2, orthogonal complement of range space of A. Then we compute V2 Hermitian A exponential J2 pi F and compute its two known inverse. Compute this. So you see, if F is 1 over Fi, then this should be 0. It should give you a large number. So you search the F, okay, you search F. So the algorithm is simply compute the SF. You search your F, and you check out the SF value. And you should see something like this. So if you see these peaks, which means it's a correct frequency. Okay, it's a correct frequency. So you search it and you check out this figure and you find out its peak value, the corresponding F for these peak values. Then that is a frequency estimate. Okay, then you can increase your resolution by reducing your by improving your the searching the grid. You can make smaller grid, right? If you want, right? If you want. So then that's this algorithm. Okay. So any questions for this music? It's very classical, but very elegant, right? And there's some other variations. There are many variations for this music algorithms. Okay. From here, actually, you see from where? Yeah, I erase it. From the eigenvalue decomposition of Ry. Right, you see that the larger D is, if K is fixed, okay, the number of souls fixed, the larger D is, the performance in general is better. But given a fixed length of T, right, the larger D is means the smaller number of samples, vector sample you can have to compute the correlation matrix, and that will make the noise not like an identity, the correlation part, right, about the noise. So it's a complicated trade-off. Okay, if the noise is very small, it's negligible, then for larger D is performance, you will see better performance. Okay. Any questions? And in the assignment, we will let you to apply the same idea to another application in array signal processing. So basically, you also the algorithm is similar. Okay, algorithm is similar. Let's look at another application. It's also quite interesting. Is Euclidean distance. Euclidean distance matrix. So what this problem is, Euclidean distance matrix. What is problem? The problem is that we have a collection of points. Okay, here is real value for the n points, and they are the Euclidean distance between any of them. So we have this Dij. Okay, it's a distance between xi and xj. Okay. Then the problem is, the task is, we only have this Dij. We only have this Dij. We know that there's n points, and we know the interdistance between any of them. Okay, and then we want to find out x1 to xn. Find out x1 to xn. This is quite weird, right? For example, in chemistry, this is a molecular conformation problem. This molecular conformation problem is that by some experiment, they can measure the distance between any of two molecules. 它可以量到两个分子之间的那个距离，然后他想要重建出这个分子长什么样子。OK， 所以就是你知道有 n 个点，然后你知道任两个距离，然后你要重建出它到底长什么样子。OK，you see that's a problem. So it's like this is maybe like this, right? You can measure the distance between any two of the molecules. And now you want to construct what this molecule looks like. Okay, so that's equivalent to find out, given this Dij, you want to find out x1 to xn, right? Also, the other one is like in the sensor network. Doing this localization, you want to locate where these sensors are. So in this sensor network, right, these sensors, they're on the ground, they are everywhere. And these sensors, they send signals. Then the others can receive the signal, then by the traveling time, right? They can measure the distance. They can measure the distance, okay, between any of the two sensors. Then you want to find out the exact locations of these sensors. Okay, need to see that problem. Okay, so this is the problem. You only know the distance between any two nodes, and you want to find out where is exact these locations. Okay. So that's a also very interesting problem, right? So how can you see the PSD matrix can play a role here? So now we have this Dij, right? Then we let this Rij is a Dij square. Okay. So we let R is a D by D N by N matrix, right? With the Rij, each Ij's entry of this R matrix. So R is this Euclidean distance matrix. Okay, so R is a Euclidean distance matrix. So each Rij is Ij's entry of this capital R matrix. Okay, the Rij is Dij squared. Dij squared. Okay, so Dij squared, that is xi minus xj squared, right? So it's xi squared minus, right, 2 times xi just was xj plus. Right. Then by this simple equation, we can connect this Euclidean distance matrix with this x1 to xn. Right? We let x, right, which collect this x1 to xn. Right? Then you can see, you can check by yourself. It's quite easy. You can check that R can be written as 2 times x transpose x plus 1. And here is a vector code. Transpose. So what this notation means, this DIAG x transpose x is taking the diagonals of this x transpose x, okay, into a color vector. So this is x1 it should that x1 is non-square. Okay, so this vector. Then based on this, okay, you construct the R, and you can find this is this. You can find this is corresponding to this one. Okay, and this one will correspond to this guy. This one will correspond. Okay, when you put Rij into a whole matrix, okay. So R can be written like this. Okay, the Euclidean distance can be written like this. Then when I talk about these two applications, you should come up with the question that obviously we cannot uniquely find out the x, right? Because even this, right, you can rotate it, distance still the same. You can shift it, the distance between it still the same, right? So you see, the problem itself, right, has ambiguity up to rotation and shift, right? Itself has ambiguity up to rotation and shift. So right, estimation of x is subject to translation and the rotation ambiguities. Right? You obviously you can rotate, you can So this means if X is a solution, if X can satisfy this, okay, given R, then X plus B1 transpose, or X multiply with Q. Okay, Q is orthogonal, and B is any constant. Okay, the X plus B multiply one transpose, which means each of the x1 to xn all are shifted by B, right? And this one is doing rotation. So if X is a solution, then you can check. If X satisfies this, then this also satisfies this. This also satisfies this. This one is quite obvious, right? Are also solution. Also solution, right? So to fix this one is quite easy, right? Without loss generality, we can assume one of the node, right, is at the location 0, for example, right? Then in this molecular, this is fine, right? Because there's no 没有一个绝对的位置。But for this sensor network, right? Then in this application, you need to have some so-called anchor nodes. 有些锚点 okay? And these anchor nodes, for example, one of the anchor nodes, you know his exact location. 你知道它的确切的位置 ，OK？ 有一些参考点。那么你得到的解，你知道会有这些 location， 你就把它 fit 到，至少那个参考点要对，对不对 ？OK。Any questions here? So suppose one of the is an anchor node, we know its location, right? Or in this molecular conformation problem, we assume one of the node is at origin 0, right? So we can, without loss of generality, we can assume x1 is at 0 location. Okay, that's why 0 location. Then we can avoid this translation, right? So that's one. It's at 0. So then the distance between the first node and others, right, we call it R1. So R1, X1 minus X1, X2 minus. So R1 is also the first column, first row, right, of capital R, right, R1. So you see, the first one, of course, will be 0, right? And here, because without loss generality, assume x1 is 0, then so this is x2 non-square. And here will be xn square, right? And R1 is known, right? Because we know R, right? R is given, R is a given distance. So R1 is known. So this is known. Okay, so this means that by assuming x1 is 0, then the 2 known square of x2 and 2 known square of xn squares is known, okay? Because they are in the first column or in the first row of capital R. Right? then the diagonal, this x transpose x, this vector, right? This will be 0, and x2 non-square, x3 non-zero to Sn non-square. So this diagonal S transpose x will equal to R1, right? Equal to. So this is known, it's given. Okay, it's given. Which means in this equation, okay, right, we can write this equation. So we can write R equal to, right, 2 minus x transpose x plus 1. And here is diagonal, x transpose x now, and B is R1 transpose plus. Here is R1, 1 transpose. Okay, so diagonal, this guy, x transpose x now replaced by R1. And this is now become given, it's known. Okay, so R is known, this also is known, right? Right, this is given and known, right? This one now is known. Okay. So then you see, right? Which means then x transpose x is half, right? It's minus half of R minus 1 R1 transpose. Right. So if we call this G, then you see X is what? It's a square root of this matrix G. This matrix G, right? It's a square root matrix or matrix G, right? So we can do the EVD of G, right? So we can apply the right. And here I should mention that you can see the rank of this guy is D. Okay, it's D. If we assume all these endpoints have different locations, okay, it's just because each x is D by n, okay, and with full rank, okay, because in general n is larger than D, right? D, for example, is 3 in 3D coordinate, right? So this is full rank, full count rank, so its range space is as x transpose, so its rank is D. Okay. So you apply EVD to G, so you see that, right? The EVD of G you can write as v1 v2 lambda 1 0 v1 Hermitian v2 transpose, because all real value here. Okay, and this lambda 1 is d by d. Okay, this is n by d. Okay, n by n minus d. So v1 lambda 1 v1 transpose, right? So then you can use v1 lambda 1 square root lambda 1 square root v1 transpose. Right, you can use this as an estimate. An estimate of x, right, by lambda 1 square root v1 transpose. So that's it. Okay.当然这个还有问题啊 right? It's still a problem. So any questions here? Right, because from here, right, this part is given, and we see the x is the square root of g, right? So we can obtain an estimate of x, right, by EVD, right? By EVD, we can find out its square root. Find out its square root. But of course, square root is not unique to mention, right? And also because in here we assume only one point is given, so it's still subject to a rotation, 对不对？就像这个点知道，你还是可以这样沿着这个点两转嘛，对不对 ？Still subject to a rotation, right? So to fix the rotation in practice, you need more anchor points. Okay. In sensor network, you need more. 在这个 molecular conformation 的 problem 不需要。Okay. But for the sensor network, you need more anchor points. So which means you have some points that you know. For example, you know that the S2, S4, S5, okay. 简单一点 ，1, 2, 3. Suppose these are known. First three are known. Okay, they are anchor points. We know his exact location. But by this EVD, we get this, right? So what do? We solve a problem. We try to rotate, right? Our x1, right? x1 has S2, 3, S3 has its first three estimate. Then we try to find a Q, right? Find this Q and to minimize, right? And subject to the Q is a unitary matrix, right? 下一步你就是去做这个 right? So if we want to find the exact location, then you need more anchor points. Okay, and you find the Q so that to fit, okay, find the proper rotation that you can fit these anchor points. Okay. We will talk about how to solve this problem in the future. This problem is called Pruskruster's analysis. 这个 Pruskruster's 是一个希腊神话里面一个人名。那个故事是讲，这个就是说你现在有个矩阵，这么一个矩阵嘛，那你要 rotate 把它 fit 进去。这个为什么叫这个？这个神话故事听过吗？就好像就是他拿一个鞋子，对不对？ 推什么？大声点。推石头那个，我不知道他具体故事，但是他跟这个有关是在于说，好像他宙斯还是什么给他一个什么鞋子，根本不合脚，他硬要把那个脚塞进去，就是要把他的脚 fit 进去那样子，就是讲这个 fitting 的，所以我印象中这个名字，你可以查一下这个问题。OK， 那就是有个神话故事跟这个有关，所以就取这个名字。OK，we stop here。
问一下，那个今天讲的那个 stature 的那个算法，就是它会就正常我们对任何一个 signal 都可以 apply 这个东西吗？还是说
什么叫任何一个signal？
就是任何一个，就是我们知道那个
对对对，屏幕分析，对对对，任何一个持续性，
就是它在什么情况下会那个 fail 吗？就是什么时候？
但你这里面有一些假设啊，你要知道 K 啊，你要知道有几个频率。
就是那几个假设。
对，
基本都是会。
还有噪声不能太大，这个算法它其实对噪声，虽然它比一些更naïve一点的方法，它的抗噪声能力是比较好的，但是它在低噪声的情况之下，就是低噪声比的情况之下，它还是很受影响。对，
所以那个算法的一些 variation 就是怎么样去估计那个噪声，然后
有一些第一个是怎么去估 K，比如怎么把 K 给找出来，如果噪声低的话，另外一个就是说怎么样提升它的抗噪的能力，然后对，这样子，对。对。你是用的 S1 能力，后面哪地方用的？就这里啊。然后这个，所以这个我就可以用来表示，R1来表示，对不对？对。然后还有就是一个这个，最后刚才也说了，我们现在那个 FS 其实不算结束，说对，你可以再旋转，对，你可以再旋转。这个我在想说，如果 X 当中只要有3个点被旋转好，比如说现在整个网络是吧？这个网络只要有